Okay, so we're very happy to have Ali Enayat back for part two of his talk on Tarski's undefinability of truth theorem revisited, I believe was the title. Go ahead, Ali.
Yeah, thank you very much, Adhar, and thank you very much to the patience of all of the participants, both the ones who were with us last time, and also I noticed some new faces, which is great to see. Just like a TV series where you have to do some sort of recap of what happened in the last episode, let me give you a rough idea of what happened, because what happened is also obviously relevant to what we're going to be doing today. So the talk as a whole has two parts. We did part one, and we just got our feet wet with part two. So part one revolves around Tarski's undefinability of truth. Part two is about this recent work that Albert and I did. And as far as the relevant parts of part one, I'd like to say that I have revised my slides, I should say, not only caught typos, but also added a few based on the questions that were being asked up to the point that we covered. So, in particular, some questions came up about the system R and Q and PA minus and how they differ. So here we're looking at the axioms of R. Well, their axiom, as you see, looks like finitely axiomatizable, but R1 already is infinitely many axioms. So M and N are varying over natural numbers. As you remember, R is just knows elementary arithmetic. Q is smarter. It actually is finitely axiomatizable as opposed to R. And then PA minus is the one that is more familiar to many of us, because PA minus is, for example, used in Kay's book on Models of Arithmetic. It describes the non-negative semi-ring of ordered discrete rings, basically. It's a stronger theory. It was PA minus that we saw happens to be sequential. We saw in the sense that the theorem was mentioned by Emil Jajapek, a remarkable theorem, whereas Q is known to be not by a theorem of Albert Visser. Okay, now in terms of other new aspects of what I just want to quickly point out, I put the semantic form of Tarski's theorem. Let me just put it on the screen here. As you see, the proof is extremely short. And then there's a comment at the end, the last bullet item, that the proof is reminiscent of the proof of Russell's paradox, as well as the proof of Cantor's theorem, which was about 10 years earlier. Now, Raman asked me a specific question of, what kind of source do I have for this to be attributed to Tarski? And I said, actually, I don't have a source. It seems to have been in the air. I started looking for sources. I found something. Well, one source, of course, is a very recent source, which was Raman's own paper on Tarski's theorem, where a quick argument by Jim Schmerl is mentioned about, basically, which is pretty much this proof you're looking at here. And then in the little bit of search that I did, I found Kripke's formulation in his lecture notes. So Kripke's formulation is, he attributes it basically to Cantor. So if you just want to hone in on the definition here, he defines what does it mean for a family of sets, given a set capital X and a family of sets subsets of X. So F is a family of subsets of X, and R is a binary relation on X. Then he defines what does it mean to be supernumerating F and enumerating F. Supernumerating F means for any S in the family, there is a cross-section. There is an X in X such that the cross-section of R is equal to X. The enumeration is stronger because it also requires not only to supernumerate, but also for each X, each cross-section to be in F. So with this quick definition in mind, his formulation is the following two conditions are incompatible. R supernumerates F, and the complement of the diagonal set is in F. And the proof is very much like the proof on the previous page. It's a very, the whole, I would say, credit goes into just formulating this principle in this particular generality. And if you come up now to the top of the page here, he says, he talks about arithmetically, well, definable sets, and he points out that to see that there is no arithmetical relation that enumerates all arithmetical relations, basically, this principle can be invoked. So this principle is just a slightly more general set theoretic formulation of what was at work on the previous page. It also connects up to recursion theory, which is also on this page. This also reminds me of when Raman asked the question from me and I gave the answer, then Raman asked the same question of Dave Marker, and Dave made some remarks which are very similar to what Kripke is mentioning on the top of the paragraph here. There's also this body of work, by the way, of looking at diagonal arguments in a very general setting. I think the oldest one I know of is Laubert, who did it in category theory, and then his work was simplified and extended by other people. And there's also a paper by Chaim Geifman about the same topic, but his setup is not using category theory. Okay, so the semantic form we saw has all kinds of consequences. Then we got to the syntactic form. For the syntactic form, this is the form that basically is the form we're going to be needing it for our theorem. It's not the semantic form. It's the famous undefinability of truth in the following sense. In Tarski's formulation, is extremely I would say, generous in its assumptions. You have a mapping of natural numbers to closed L terms, where L is a particular language that you fixed ahead of time. So they don't need to be numerals, hence this unfamiliar notation that I picked. You also have an arbitrary one-to-one correspondence between formulas. We just need them for formulas of at most one variable and natural numbers. I've used the hash notation to indicate this is not necessarily the Gödel numbering, it's just any one-to-one correspondence. And the inverse of this mapping is n maps to phi sub n. This is this notation is Tarski's. This lowercase n and hash is my notation, but pretty much everything you see on this page and the next page is Tarski's. Then you can talk about the diagonal function, which is the result of basically sticking in the representative for n into the nth formula and then taking
that's the syntactic substitution, right?
Exactly.
This is what I was exercised about last week, and I even went back to Yek to see where this was bought. But yeah.
So basically, typically speaking, this is done in courses on formalizing Gödel's theorem or representing recursive functions in formal systems, whereas here the setting is extremely relaxed. And
you're not in any way trying to arrange that delta be definable, and
that's right.
Disturbing me, but apparently you don't need that.
In a way, those are built into the theorem itself. Basically, it says if you have such a function, such a mapping of natural numbers to syntactic objects, and this mapping phi going to hash of phi and its inverse rather, then on the basis of that, you can define the diagonal function. So that's this bullet item. And then you also have you have a notion of what does it mean for a function from omega to omega being the natural numbers, of course, to be t-definable, and what does it mean for a subset to be t-definable. So these days we refer to these as representable, but Tarski uses definable. So I stuck to that in case you happen to go back to Tarski's article, as opposed to t-definable. And then the
Oh, sorry. Wait. Yeah. What is that Blackboard bold F? What F? What is this?
Oh, yes. So this is the result of applying. Yeah, good point. This is the result of applying. Given this n, you apply f, which is this function, to n, and then you get a natural number, and then you take a representative of it. That's
okay. I thought somehow thought it was an extra.
No, it's just kind of a suggested notation.
It's thinking of f of n, computing it, and then Blackboard bolding that.
Exactly.
Okay. I was fine. It's not a new piece of syntax. Good.
Yeah. Right. So far it's basically pretty much standard way of handling functions and subsets of omega, mapping it to syntactic basically objects. And then the syntactic formulation version 1 is that if you take the codes of provable sentences from T, so given a theory T, Tarski uses V because he talks about a particular sentence being valid in the theory T, and what by that he means T proves, you can prove phi in T. So I stuck to his notation, but stuck this T here as a subscript to remind ourselves that this V depends on T. So if you define it this way, as just the codes of the sentences that T proves, then Tarski's undefinability of truth theorem, as is itself done in his original 1953 work, is that if you assume T is consistent, then you cannot have your cake and eat it too. And having your cake is having the diagonal function being definable, and eating it too would be the set VT to be definable. So one of them has to go. As you see, Kripke's formulation was informed by this formulation because he also had this formulation. You cannot have both of these situations in his little semantic formulation that I just showed you. And then as a quick corollary, we get the usual, more familiar formulation of undefinability of truth, which is this formulation, that if you have a consistent theory in which delta, the diagonal function, is definable, then there is no formula theta of x with this property, that theta is true of the code of the formula if and only if that formula is true. And then the other corollaries follow, but this particular corollary that we're going to be needing for application to what we're going to be doing. I'm going to, now that the slides have been revised and the talk is going to be over today, I'll be more than glad. I mean, I was glad already, but nobody wrote to me, so I was kind of waiting for anybody who needs the slides. But I'll be sending the slides to Athar when I'm done with the talk, and you can look at these at your leisure. In particular, I don't want to go through this proof. This is the proof of the syntactic version. I cleaned it up a little bit, put some color. It's now as clear as can be. It basically, as you can see from the presentation, is much longer and more complicated than the semantic proof. And also it requires more finesse at work. For example, we didn't need in the previous format, the semantic format, we didn't need the Gödel numbering, so to speak, the code to be one-to-one. Here, we need some sort of inverse map to go back and forth. And the thing to have in mind is this is a formalization of the Epimenides liar paradox. Okay, so this is exactly what was Gödel's intuition, and Tarski himself gives credit to Gödel, except that his formulation, meaning Tarski's formulation, is much cleaner and much somehow goes to the heart of the matter, takes away the arithmetization and sticks with what I call numberization. There are no arithmetical operations, that are at work. You're just objectifying syntactic objects and what I'm calling numberizing.
And no fixed point, really, right?
Yeah, the fixed point in a way is done in the middle of the proof. That's right. That's right. There's no appeal to a fixed point argument, but you're in effect building the fixed point as you go along. Yeah. We went through these slides last time, so I didn't want to say much about them, but let me come back to, now this is beginning of part 2 of the talk, where I gave the motivation for the Theorem A we're going to be looking at. Theorem A is the main theorem in the paper with Albert, and then once one understands how Theorem A works, then the other theorems follow fairly quickly based on the same strategy. So the question was, is there a consistent completion of PA minus that is axiomatizable by a set of sentences of bounded quantifier complexity? As you recall, this question asked by Stefan Lemp and Dino Rosiger in the context of their joint work with Uri Andrews, David Gonzalez, Hongyu Zhu. And the theorem they prove has to do with Borel complexity of classes of models of a particular theory. And it's condition number 2, that basic condition number 1 is very technical, and I know Dino already gave a talk at MOPA and talked about this result. the motivation for asking the question had to do with item number 2. T does not admit a first-order axiomatization by formula of bounded quantifier complexity. So hence the question, does it work for PA minus? And as you recall, I put the reference also in the bottom of the page of their paper. As a way of warming up to this question, I spent some time talking about the instances of this question where T is replaced by other theories. For PA minus, it wasn't clear, but for other theories, there's already actually some interesting machinery goes into answer them. In particular, this is a good place to also, before we look at other theories, to distinguish between, well, we talked about both the sigma n hierarchy of formulas for arithmetical formulas. This is the usual one we see in arithmetic, where a bounded quantifier doesn't increase the complexity of the formulas. And this is the top one. I just cut and pasted from Hayek and Putlock. This is nothing exotic. This is what you all have seen for the arithmetical hierarchy and arithmetical formulas. The one at the bottom, I've cut and pasted from Albert's paper on the one that I guess I didn't reference it directly in the talk, but it's in the paper. Basically, this is where the main fact F is going to be borrowed from, as we'll see fact F in a few minutes. But before we get to that, so these are the notation for it puts a star on the top of the letters sigma and pi as a way of distinguishing from the familiar arithmetical hierarchy of formulas. And this is counting the depth of quantifier alternation. And so the recursive clauses here, this at stands for atomic formulas, also expanded by having a particular constant for truth and falsity, verum and falsum. So a formula is in this category or in this class, sigma n plus 1 star, if it's atomic, or it's a negation of a pi n plus 1 star, or of this form, or of this form, or of this form, or of this form, or of this form. But the intuition is that we're counting the depth of quantifier alternations. Going back to the question of Dino Roseger and Stefan Lemp, for true arithmetic, the answer to the question is in the negative already by the classical hierarchy theorem of Kleene and Mostovsky, which they proved back in the 40s that the arithmetical hierarchy does not collapse. For PA, this was done by Rabin in 1961. For Rabin, the result is stronger. It actually says no consistent extension of PA. It doesn't have to be complete. And this is, the top one is a complete theory. This one is, we don't even have to have a complete theory. No consistent extension of PA in the same language is axiomatized by a set of sigma and sentences for a fixed n. The idea was that this was a model theoretic proof. It was already refining a result of Ril-Nardzewski from 1950s who showed that PA is not finitely axiomatizable. So Rabin's and Ril-Nardzewski's result are summarized in a new format in Theorem 10.2 of Kay's Models of Peano Arithmetic book, if anybody's interested in looking at those model theoretic proofs. But this model theoretic proof doesn't work for our case. It is something specifically which works for PA. So this is basically the wrong place to look for generalization when it comes to seeing what to do for PA minus, for example. Let's see. Yes, and then this other way of looking at Rabin's result is going to be useful. So Rabin's result was proved using model theory, but then it also can be done using other machinery, in particular proof theoretic machinery, which is basically cut elimination theorem, partial satisfaction classes, and Gödel's second incompleteness theorem. So this is done in Hayek and Putlock's book in Theorem 2.36. Generalizations to inductive sequential theories. I mentioned this last time. Yes, please.
Are you able to say a little bit about that Hayek Putlock machinery there?
Yeah. Basically, the idea is that if there was a sigma n, so suppose you had an axiomatization by sigma 10 sentences. You have a bunch of sigma 10 sentences, and of course, not, you know, it's an infinite set of sigma 10 sentences, suppose. And you want to show that these cannot possibly axiomatize PA. The idea is to then get hold of a sigma 10 truth predicate, and then use the sigma 10 truth predicate to show that PA can prove the sigma that the true sigma 10 sentences as a whole are consistent. So you're basically, that's pretty much Mostovsky's reflection theorem. And if PA was axiomatizable by sigma 10 sentences, then this would show that PA would be able to prove its own consistency, which would then contradict Gödel's second incompleteness. So this is kind of high-level summary of
it. Thanks. So that makes sense.
Yeah. Yeah. So this machinery on the first bullet item was extended by Montague to a more general setting where you're looking at inductive sequential theories. We briefly saw sequential theories last time, what the definition. Here, an inductive one adds a lot of oomph power to the theory because you can do induction on the natural numbers of the sequential theories. And the relevant hierarchy here, because we're not in the arithmetical context anymore, is the quantifier alternation depth that we just saw with the one with the star on the previous slide. And therefore, as a summary, if we want to look at the cases that were known prior to this theorem you're going to be seeing, there were basically inductive theories, either Peano arithmetic, Zermelo set theory, or Zermelo-Frankel, its extension, second-order arithmetic, Cayley-Moore set theory, but not Gödel-Bernays or not ACA0, things that don't have full power of scheme of induction. Now, as far as sequential theories go, we saw basically that their history in a way goes back to Gödel's use of the Chinese remainder theorem to be able to build sequences within PA. And as I mentioned earlier at the beginning of the talk, not too long ago, Albert showed that Q is not sequential, and Emil Jajapek showed that PA minus is sequential. So this sequentiality of PA minus is going to play a key role in the answer to the Lemke-Rostiger question.
Ali, I probably should know myself, but it is a remarkable paper of Jajapek. Is he using some elementary number theory as well? Something like Chinese remainder theorem?
No, I think, well, he's definitely doing a lot of clever stuff, but since you're asking the question from somebody who in the audience would know a much better answer, I'll have Albert answer that question.
Yeah, so he uses precisely Gödel's beta function. And in some sense, it seems to me that establishes that Gödel's function, the beta function, is still the best way of doing decoding of sequences in the context of arithmetic, because Emil does miracles with it in this extremely weak context. But again, one important thing about the clue, so how does he get away with it? The point is that the numbers for which you can do the projections are a definable cut of the PA minus numbers, right? So you cannot do beta projections for all numbers, but just on a definable cut. So that's I think some part of the secret how he's able to get away with this, because I'm still very much, well, I was very much surprised, and the surprise lingers still that he could do this.
No, it is remarkable. I wonder if Gödel could have proved it if he wanted to.
Well, he really, what was missing, of course, is the Solovey's shortening of cut idea. But if well, Gödel would have been able to find that for himself. So yes, Gödel clearly could have done it.
Okay.
Thank you.
Sure. Yeah, so just as a quick reminder, because we're going to be needing a little bit of having some intuition about sequential theories, that sequentiality has various manifestations. One manifestation is basically in terms of adjunctive set theory, but for our purposes, the way I'm going to be setting up the proof is more helpful to think about the original formulation, which has to do with having a designated formula, n of x, for natural numbers. So your theory is able to talk about a part of it basically behaving like a model of arithmetic. And on that n of x, you have arithmetical operations of successor, addition, and multiplication. And then, and of course, the question is, how much arithmetic would we expect for this to be satisfied? And we just need, for the purpose of the definition, the actions of Q. But it turns out, because I delta 0 is interpretable in Q, that automatically we could already shift to another formula where I delta 0 is true by Rilke's theorem. But as far as the definition goes, we just need Q. As far as the sequentiality bit, there is a particular also designated formula, beta, again in honor of Gödel's beta function, which is, as you see, is a ternary formula whose intended meaning is that x is the ith element of a sequence W. And the axiom that we need is that T is able to prove every sequence can be extended by any given element in the domain of discourse. So the point to emphasize is that these sequences are not sequences of numbers necessarily. What makes sequential theories powerful is that these sequences are sequences of objects in the domain of discourse. So in a way, the numbers can talk to the objects in the domain of discourse via the sequence coding, as opposed to just sitting in a corner of the universe and not communicating with the rest of the universe.
Once again, sorry, this is something whoever knows about this, I want to talk about. I've been trying to chase down something like that literally in the case of algebra, finite dimensional algebra, for ages. And surely it can't be, but anyhow, but I mean, so if maybe talk about it later.
Well, yeah, I think the problem is that these sequential theories are quite rare in just algebraic settings. I mean, it depends on how much, so for example, already with plus and times, you can cook them up, but depends on the algebraic format, right?
Yeah, you can try to formulate one though. I just don't, maybe there's a right and the wrong way to do it, but just some sort of, neatest thing that would allow you to talk about arbitrary n tuples in, an algebraically closed field or something, having both the quote numbers there, which would have their own internal representation as, complex numbers, and also, and somehow be able to leverage the completeness, for any fixed size of a vector, you still have completeness. And then anyhow, it's just been something I've been trying to chase down since forever.
Yeah, okay.
I'll send you I have a Math Overflow post about this from like 10 years ago.
Oh, okay. Then in that case, maybe I can add something to it. Yeah. Okay.
One or two of them. Yeah. Okay.
So I already mentioned that the numbers in a sequential theory can be required to satisfy a delta 0. And then we saw Albert's theorem about partial satisfaction for formulas of a bounded complexity, where the complexity is quantifier alternation depth. And as I mentioned before, this was fine-tuning work that was, so this is basically a beautiful sequence of better and better results, which started with Pavel Putlak, who did it for logical depth, and then Albert, who extended that further to quantifier alternation depth. And then, so the theorem, which we call fact F, let's just look at it again. In the context of a sequential theory that is formulated in a finite language, and again, language for us is signature. If you fix a natural number, then the following is true. Of course, you also want to fix an interpretation of arithmetic satisfying I to the 0. So we assume that is given. We have a fixed natural number, and we have a fixed interpretation of arithmetic satisfying I to the 0. Actually, yes, I think this is good enough. So what is part A? Part A is basically saying there's a definable cut I sub n of n. So what does this mean? It means there's a particular formula that defines an initial segment of the numbers of the interpretation for arithmetic. And it turns out what we need is not just for this cut to be closed under arithmetical operations plus and times, but also we want it to be closed under what's known as the omega-1 function, which sends x to x to the power log on base 2 of, let's say, x. So it's known that this particular function can be assumed to be also total on this interpretation n. So this is now kind of a technical part of it. So I'm kind of being purposefully vague, but the idea is that this cut is a cut of the natural numbers. Just for the all intents and purposes, think of it as the cut in which you can do syntax. And along with this cut, there's a formula, sat sub n, which depends on the n that was specified, such that provably in the theory, sat sub n satisfies Tarski's compositional clauses. As long as this sat of n of x, think of it as the formula coded by x is true given the assignment y. So this x is a formula, y is an assignment of objects to the three variables of x. So the Tarski conditions should be true for any x in sigma n star, which happens to be living in in. So this is now a sentence which says...
It could be non-standard then, right?
Absolutely, absolutely, yes. Yeah, because we want this to be, it's just basically one sentence which is quantifying over sigma n star formulae in in. Yeah, and for all variable assignments. So this x will be limited to sigma n star formulae, but the assignment y is allowed to go all over the place, all over the universe. I mean, objects of the universe can be substituted for the free variables. And then what we need from this actually is part B, is that there's another formula, which is a sibling formula, which is for the truth predicate, truth sub n of x, such that provably in T, truth sub n is extensional in the sense that it respects the equivalence relation representing equality in the interpretation of numbers. And the important property it has is that for all models M of T and for all sigma n star sentences, we have this equivalence. It's a truth definition. Now here, psi is a standard formula because we say M satisfies psi if and only if something happens. So this psi here is all, this claim is about all sentences that are sigma n star. I'm recalling it a typical sentence psi. So there's a truth definition for sigma n star sentences. And the pedigree for this was on the next page, that basically what Albert's theorem then, this fact F gives us is, I'll just put the whole thing on the page here, is a long story which started in the 1940s with the sigma n completeness of the nth jump of 0. And it worked through various improvements and refinements by Mastovsky, Montague, Levy, Geifman, and Dimitrakopoulos, Purlak, and now Albert Visser, who is, of course, today with us. Okay. All right. So now let's look at Theorem A. We saw the statement last time. It's basically this theorem gives a negative answer to the Lem-Prosser question. Any consistent sequential theory formulated in a final language that is axiomatized by sets of sigma n star sentences is incomplete. We have fixed n, and so basically you cannot have a bunch of infinitely many such sentences whose deductive closure is complete. Okay. So let me look at my time. Yes, we're doing well. So we're going to go through this group. There are 3 pages of slides here, and I'm going to go through it methodically, so hopefully everybody will be able to follow. So we argue by contradiction. We say suppose T is a consistent completion of a sequential theory in a finite language. And the theory, of course, T is sequential. because any extension of a sequential theory is sequential. And suppose to the contrary that there is some n such that sigma n star sentences axiomatize, a bunch of sigma n star sentences axiomatized T. So this, therefore, is summarized our assumption in item number 1 here. So this n in blue is the n, for example, think of 10 as our number. So there is some number 10 such that there's a set A of sigma 10 sentences that have the property that they axiomatize the theory T. That's pretty much item number 1. I'm stopping here and stopping at N and A because both N and A are going to make an appearance on the other pages. So just remember the N we're talking about is this 10, for example. And this A, this blue A, is this bunch of sigma 10 sentences that claim to axiomatize our sequential theory. Our proof by contradiction will be complete once we verify claim heart below, since it contradicts Tarski's undefinability of truth theorem. So we claim that actually there's a unary L formula, phi of x, such that for all sentences psi, we have psi if and only if phi holds of the code of psi. So this is precisely what Tarski says. The syntactic form of Tarski's theorem says it's a no-no. So once we prove claim heart, we will be done because Tarski says this is a contradiction. So our claim, the proof would be finished if we prove claim heart. Okay, it's an equivalence, so it's going to have, the proof is going to have 2 parts. Now, before we get to that, to prove the 2 parts, we're going to take advantage of sequentiality to get hold of a formula. So look at this formula here. It has 2 variables, pi and x. It has a subscript here, true sub n, which it's a way of just keeping track of what this formula is saying, but it's a formula in 2 variables with the property that for each standard sentence psi and each standard pi and each model m of t, we have the following. M satisfies that this formula holds for pi and the code for psi, if and only if in the real world, pi is a code of a proof of psi from this set of sentences, the set of true sentences that are in sigma n star, basically, the true sigma n elementary diagram, or sigma n star elementary diagram of M. Let me pause for a second here just to make sure we're seeing what's happening here. I'm assuming that our sequential theory, which has an interpretation for numbers, because this has an interpretation for numbers, this M need not be, of course, a standard model. And of course, in most interesting cases, it's not going to be. But it does have it is going to have an initial segment of objects which are standard, that are well-founded. So I'm assuming we replace them without loss of generality with just their natural counterparts. So basically, we're assuming that omega is just an initial segment of the numbers of this sequential theory. Hence, when I'm using pi here and this Gödel numbering, they're elements of M in the sense that I just described. I'm just identifying the well-founded part of the numbers of M with basically omega, or if you want to think of it even more generously as V omega, because if you want to talk about sequences. Yeah. And so we have a faithful representation of this relationship that if the model would satisfy this property, if and only if for a standard pi and a standard sentence, if and only if in the real world pi is really a code of a proof of psi from this set of sentences. Again, notice this is a standard set of sentences because pi is a standard proof. No non-standardness is happening here. Interestingly, non-standardness is going to come later in a manifestation, but at the very end of the proof. Okay, so as you remember, we had this claim heart, which was contradicting Tarski's. The idea was that we have a truth predicate, and the candidate for phi of x is, again, let's go back to the previous page. I said there's a formula phi of x, which gives a truth definition. For our candidate for this phi of x is this rho of x in honor of Rosser, which expresses Rosser probability from the true sigma n star sentences. So what does this formula say? It says rho of x says there's a y such that y is a proof of x. Remember the way it works. The first element in the proof relation is a proof. The second one is a formula. So this relation says that y is a proof of x, but not just in first order logic, but from assumptions that are in true sub n. And for every z less than y, z, if you decode it as a syntactic object, is not a proof of the negation of x from the same set of sentences. So this is exactly Russell provability, that I have a proof, but no proof shorter than me proves my negation, basically. That's the way we think about Russell provability. So you might say, okay, so far everything is kind of going intuitively, but why Russell provability? Well, it turns out we first tried out ordinary provability or cut-free provability, and that didn't do the job. So the next best thing is Russell provability, and that worked. And of course, it's a classic trick. So our goal, remember, is to show a claim heart, which is that psi holds if and only if rho of the Gödel number of psi. And I'm presenting this proof model theoretically, this equivalence, by saying this equivalence holds for all models, but this proof can be reformulated purely in terms of the theory T. It's just for gaining intuitions that and also because I prefer working with models, and Albert, of course, likes to work in theories, and that's why we often match up, because it's the left and the right eye coming together to see things in more in focus. Okay, so we take a model of T, and we want to prove this equivalence. So we're going to first prove the left to right relation. For all sentences psi, if psi holds, then rho of the Gödel number of psi holds. Okay, so let n and a be as in 1. Remember, n was 10 for our case, just for easiness, and a is a set of sigma 10 sentences. And of course, with the way we chose a, because they're axiomatizing T, and M is a model of T, A is a subset of the true sentences as computed in M, which are of complexity sigma n star. Okay, as you see, it says Theorem A concluded. So on this page, everything is going to come to a conclusion. But assumptions about T, that was because we assume that T is complete and A axiomatizes it. There are finitely many axioms in A such that psi is provable from alpha 1 through alpha n. And therefore, let's take a code of a proof that witnesses this probability relation here. And then thanks to 2, which 2 had to do with faithful representation of this relation of something being a proof of something else, as long as the somethings are standard. Because in the real world, we have a proof, then the model also attests to the same relationship holding between pi 0 and the code for psi. The assumption of the consistency of T coupled with 2, which was the faithful representation of this proof relation, says that for every z less than pi 0, z is not a proof of this should be actually a not psi here. This is, I think, a typo here. Yeah, this should be a not psi. Because we basically want to ascertain that pi 0 is a proof, and no shorter proof works for the negation. So there's a not is missing. Hence 3 holds. Now, what was 3? 3 was the one-way direction. Yeah. The one-way direction of basically this equivalence that is going to give us a contradiction. So this was easy. This was smooth. To complete the proof, we need to do the other direction. Not psi implies not rho of the Gödel number. And again, we assume that we have a model of not psi. And by putting 1 was basically the the assumption that there's a bunch of sigma 10 sentences that axiomatize our theory T, and M is a model of T. And since M is also a model of our theory, there's a standard proof pi 0 of this not psi from the true sigma n star sentences that are in M. So by the faithful representation theorem, which was item number 2, there's a proof pi 0 of the negation of not psi. Not psi has a proof, therefore there's a proof from the negation. Now, suppose, remember we're trying to prove not psi implies not rho of psi. Now suppose that this is false, meaning suppose that M satisfies rho of psi instead of, because we're trying to prove M satisfies not rho of psi. By the choice of rho, because rho was for Rosse probability, this means that there's a proof of psi, and for everything below M0, there's no shorter proof of the negation. This is just a definition of Rosse probability. Okay, this is no magic happening yet. Now, the key observation is that by putting 2, which was faithful representation of proof relation, with the assumption that M is satisfying not psi, it tells us that M0 in 6 must be a non-standard element of M. This M0 has to be a non-standard element because if it was really true that this relationship hold this part of it, if M was really a standard proof of psi, then M would have to satisfy psi. But we just assume that right here, M satisfies not psi. But we assumed that pi 0, because, sorry, we didn't assume, the pi 0 of 4, this one, is standard. So we have, let's see, where is this one? Yes. So let me see if I have, I just wanted to see, let's see, the ordering principles, property of natural numbers shows that pi 0 is less than M0, which contradicts the second conjunct of 5. The second conjunct of 5, yes, right here. Yes. So if M0 is non-standard, then when you quantify over everything less than that, you're picking out all the standard numbers, and in particular, all of the standard proofs. And this conjunct cannot hold this part because we have a counterexample, which is pi 0, which is a standard number sitting, which is a proof of not psi. And we're saying there's no proof of not psi. So we've reached a contradiction. So the proof is in the scale of proofs in mathematical logic, the proof is very simple. What's behind it is, of course, is that it's standing on the shoulder of giants. It's standing on these truth predicates that are available in sequential theories. And we're standing on the shoulders of Rosser, who came up with this grand idea. Let's see, anybody else whose shoulder we're standing on? Albert?
Well, Putlock, who invented this notion.
Yes, I guess I guess that whole pedigree of partial satisfaction classes. Yes. Okay. So theorem B is the theorem B would be actually more to the heart, closer to the heart of people maybe who are typical MOPA participants, because it has to do with not with sequential theories, but extensions of I delta 0 plus X, and in particular, just more familiar arithmetical theories that. So in theorem B, we're switching actually to a different hierarchy, which is the usual hierarchy of sigma n arithmetical sentences, as opposed to the previous one, which had to do with this more exotic one. Well, not exotic as much as less used sometimes in some context in arithmetic. And the proof is actually very simple. I mean, there are two proofs that I've put down here. One is that thanks to the fact that in the context of I theta 0 plus x, again, remember x is the one statement which says the exponential function is total. It is well known that there is a partial truth predicate for sigma n formulas for any given n. So the previous argument that you saw can go through exactly replacing satisfaction for sigma n star formulas with satisfaction for sigma n formulas. So that's basically the proof outline using theorem A's proof to just generate theorem B. Or we could resort to a more powerful theorem, the Matiasevich-Robinson-Davis-Putnam theorem, which says that well, it has to do with the Diophantine representability of computably enumerable sets in I theta 0 plus x. So with MRDP at your disposal, the formulas that are sigma n are equivalent to sigma n star provably in I theta 0 plus x. So we can apply theorem A directly, as opposed to saying use the strategy of theorem A. You just plug in theorem A plus MRDP to get theorem B as the corollary. And then here's a more general formulation of theorem A, hence theorem A plus. So the more general formulation here is that you have also a theory T in the background that is computably enumerable, and you want to add a bunch of sentences to it, to this theory, that are of fixed complexity. And the claim is that if you begin with T, which T, because it's computably enumerable from the point of view of computability theory, it has bounded complexity, but the sentences in T could be of arbitrary quantifier complexity. So T basically is only as an overall object simple, but its constituents could be quite complicated. On the other hand, A that you're adding to it is the opposite. It could be a very complex set of sentences as a whole, but each constituent is a sigma n star sentence. And this theorem A plus basically says if you put such two things together, such a T and such an A, and it's consistent, this theory is consistent, then there's no hope of completeness for T union A. So hence you're generalizing basically Gödel incompleteness and the previous theorem, you're kind of putting it together. And the proof is pretty much following the strategy of theorem A and just replacing the proof predicate that we had there with a different proof predicate, but it's the same skeleton. If A happens to be empty, then the proof strategy gives you, let's see, let me just slow down here. Oh yeah, the reason I put remark A here is that if A is empty and you only have a computably enumerable sequential theory, and your theory T, instead of saying is sequential, you just say that it's a consistent extension of Robinson arithmetic, then without the assumption of sequentiality, the theorem goes through. So this way you get basically Gödel's theorem using Tarski's theorem with this proof format. There's also a set theoretic formulation of or manifestation of this phenomena, which is theorem C, where if you want to think of it intuitively, I theta 0 plus x is replaced by Kripke-Platek set theory, and the sigma n hierarchy is replaced by the sigma n Levy hierarchy. Same kind of proof goes through, because for the Levy hierarchy, there are also partial satisfaction classes.
And every consistent extension, I guess?
No, it's actually completion, because because for theorem, yeah, basically theorems A, B, and C, I mean, all these theorems are talking about completions. I'm sorry, there are two ways of formulating it. You basically say you have a completion that is not axiomatizable by a bunch of sigma n sentences, or you say if you have a bunch of, yeah,
but I mean, a completion's complete, right?
No, that should be extension here.
Yeah,
Yeah,
the
yeah,
first,
yeah,
the
yeah,
first
yeah, yeah.
time
This should be
extension.
First
consistent.
completion should be extension.
Yes, yes.
That's what I
So it should
thought.
have,
Okay.
yeah,
I mean, I
this
know
should have
it's
said,
obvious. Okay, sorry to,
yeah.
yeah.
No, thank you. It's, as you caught a typo. Every consistent completion of KP is not axiomatized.
Right.
Yeah.
No, I thought there could
Yeah.
be some subtle sense I'd never heard.
No. This is just this. Yeah, this should have been consistent extension. Yeah. Very much in accord to theorems A and B. Okay, so in the abstract, I mentioned something about this. Our work was anticipated at some level by Emil Jejapek. It turns out that he had this theorem as part of a math overflow answer to a question. That question actually had to do with axiomatizations of set theory and whether something like in the presence of large cardinals, if you have some exotic large cardinals, then you could axiomatize set theory by a bunch of, let's say, sigma 10 sentences. In this case, it was sigma 2, I think. And Emil formulated this general result and answered the question. The question was not about sequential theories or about basically what although Emil, as you noticed, was the one who also proved PA minus is sequential. So Emil had complete access to this theorem if it was asked from him. Now, the irony was that when we finished our paper, one of the first people that Albert and I bounced the paper off was, of course, naturally Emil. And Emil had a very, after about a few weeks, he wrote back to us and he gave us a lot of very interesting feedback, and we fine-tuned our paper. And then another few weeks passed, and then Emil said, "Oh, I remembered that I have the same result." So it was about a month and a half afterwards that he himself had forgotten this result. And of course, Albert and I were also not aware of it. But this result you're seeing here on the page here is pretty much the abstract formulation that of our result if you of this theorem, for example, A plus, if you plug in the right ingredients, and I've given as you see, the source for that. Okay, so since my time is up, let me just say just a few words. I know if I'm allowed to go another 5 minutes, I'll be able to finish. Is that okay?
Yeah, I think that's fine. Okay,
I'll make it really quick. So it turns out that the assumption in theorem A was that A cannot be, well, was finite, and a natural question is whether L can be infinite. And it turns out there are natural counterexamples to show that if you allow L to be infinite, then the theorem falls apart. Basically, it's false, that the theorem becomes not false for certain theories. And one example is basically iterated truth. If you have an iterated truth theory, you have a T0, T1, T2, which each one is a truth predicate over the previous one, then you can get any completion of this theory axiomatized by just sentences of bounded quantifier complexity, because of basically this situation holding along the way. An arbitrary complexity can be reduced to an atomic complexity. So that's the intuition behind it. The other one, another way of doing the same thing, but using not truth theory, is to Morleyize or atomize by basically enriching your theory with predicates so that for any formula you have quantifier elimination at work. And this is usually called Morleyization these days. And by doing that, you can also get a counterexample to the theorems here when L is infinite. And then a bunch of offshoots. Probably the most remarkable offshoot is a question that is an extremely interesting question. What about completions of Q? Is there a consistent completion of Q that is axiomatized by a collection of sentences of bounded quantifier complexity? The informed conjecture is yes, but no proof has been written down yet. And then in work that Albert, Mateusz, Wojcik, and I have been looking at, we're looking at what happens if we still ask for sigma axiomatization by sigma n sentences in a context, for example, completions of PA minus. And a the first result that basically started with Albert, which has been fine-tuned to this formulation, is that there is a completion of PA minus that is axiomatized by a single sentence together with a set of sigma 1 sentences. So this is a whole leads to a whole bunch of other questions involving what happens with I open and other related questions. So that's an offshoot that is a work in progress. Albert has already given a talk at MOPA, and I'm not sure to what extent he's talked about what the bullet item I have here, but he's been looking at basic forms of Rossi probability and its siblings, which is Friedman, Goldfarb, Harrington, under minimal demands on the method language and on the object language. And the work connects up to the work of Said Salehi, who has done some sort of reverse mathematics of in this area, where incompleteness theorems are matched to weak versions of fixed point lemma. And this is a paper of Salehi that appeared in 2023. With that, I'd like to bring my talk to a close with this last slide to show you a bunch of names that came up in this talk. So this is as you see, a library card that is not used. As you know, these days we don't see library cards anymore. Hilbert's Grundlagen der Mathematik is from Princeton University, and people who borrowed it, Mostovsky's name came up, Rabin's name came up, and our friend Kurt Gödel is at the bottom of the page. Okay, thank you.
Borgozelski's come up.
Oh yeah, all kinds of. Yeah.
Is that Kreisel?
Kreisel, I don't see here.
What about
Really?
22?
Wow, that is quite
My
Beautiful L.
my hill, Rabin.
Yes,
Oh my God,
Schoenfield,
what's
William Boone. I don't know. I can't read this name. Could you read?
I think this is G. Kreisel.
that
But
could be
Oh,
Chrysler, yeah.
Okay, then Kreisel is there, and this looks like a Polish name,
that's Pogorzelski.
Right.
Pogorzelski.
That's a whole. Yeah.
Okay,
Okay.
let's thank Ali. Thank you
Thanks
very
again.
much.
Thank you.
Okay. Thanks everyone. Looks like there's some.
There is a question in the chat from Ken, so I'll start with that. I'll read it off. Ken, wrote a general question: is there any connection between some of this work and Smolian's elementary formal systems?
Not that I know of. I mean, I've seen some work of Smolian, and I have high regard for it. And I, in particular, did look at some of his expositions of incompleteness theorems, where he emphasizes how Tarski's theorem has been underestimated, and he builds a lot of his exposition around Tarski's work. But other than that, in connection with the work that was mentioned, I certainly wasn't aware of that. I'm not sure if Albert was.
Yeah, so maybe not just Smolian, but around this time there were a lot of small papers written with results and sharpenings of incompleteness theorems, and so I still don't have a complete overview of what was going on then. So the answer is probably maybe yes, maybe no. It's
That's
but
a good answer.
I don't know specifically about a direct result by Smolian that is connected to this one.
Okay. Other questions, or if Ken would like to follow up on that? Oh.
So
I think you're
Your
muted.
microphone is off. Yeah, I guess Ken is
Did
writing.
anybody after Gödel? Did anybody after Gödel take out the book, or did they sort of like retire it?
That's a good question. I received this about 3 years ago from a friend who I think was visiting Princeton, and so I didn't
The
ask
book
that
or just
question.
the PDF? I mean,
Yeah.
that's
Yeah, in the
fantastic.
PDF, yeah, the PDF is basically just this, yeah.
That's a remarkable document.
Mhm. Other questions? Okay, so let's thank our speaker one last time. So thank you again, Ali.
Thanks again for accommodating me, and it was always a pleasure to be giving a talk at your seminar.
I'll end the recording right now, but I'll just mention this will be our last seminar for the semester. Please keep an eye out for updates for the fall. There will almost certainly be some sort of technology change, as I am losing my Zoom license from my institution has decided to go with in a different direction on
I
that.
see.
So we will, I'll send out or Vika will probably send out some information when we have an update on how we'll be running the seminar moving forward.
Sounds good. Okay.